hear me? Hello and welcome everyone to the third lecture of discrete mathematics. Before we start with the content, I'd like to ask you a few questions. So in the break, I would like you to mark with a piece of chalk, like for the first week, what your workload was roughly. If you didn't do the homework, you can say 0, but you showed up, so I guess there's more than 0 workload. Or maybe you didn't show up the last week. And if you really struggled, maybe you were 30. I think above 30 would be unrealistic. So I put online this exam. So the idea is that every lecture I collect what we did, and I re-wrap this into an exam question. And then you have the exam already beforehand. So I keep updating this file. And then at the exam, I roll a dice. And then that's going to be the question for the exam. Is it understood? Yes?
I have an idea about
Yes?
if the exam
Yes. Yes. It's exactly what we try to do, but I have to ask the scheduling people to give me a room. I have to ask the exam committee to approve that thing. But yeah, we're on it. I think it makes more sense I update you once we found a solution. But that indeed makes it easy for also the re-exam. You don't have to prepare anything. But is just for clarification, did you understand how this exam will take place? And do you think it's a good idea? You don't know. You will see it. If you pass, it's good. If you fail, it's bad. So maybe let me explain the reasoning behind it. I think often the exams are more intelligence tests than actually testing knowledge, which I don't really think is very good because I wanna figure out with you. Remember the things because these things that I teach you are actually useful, and you will, if you go in the direction of discrete mathematics, you will use them later. If you go in the direction of algorithms, they will be handy later. If you become, a general mathematician, this should be part of your general toolbox of things to know, and just knowing them is useful. And I don't want to test your smartness. I just want to test if you understood what was in the lecture. That makes sense? Okay. And I want you to be able to prepare well. Next question I had, did you get along with feedback fruits? So let me first start with who got along with feedback fruits? Okay, who had problems with feedback fruits? 2 people. So Martin, maybe?
So, I handled everything. My own access.
Aha, so I see.
There are no other items.
So I guess what could happen is what we want to do is we put groups, and what happens is everyone, and maybe no one else handed in from your group. That could be, but the right thing to do would be to write an email to Nick and Gabriela.
Yes, I'll ask.
Yeah. But yeah, so I guess I put it on also that you should you should grade yourself, right? So that was just for me. I would like to try that out if that's a helpful thing for the process or not. But I guess your group is just empty, and I formed this group of 5 because the idea is that hopefully not all in your group are disbanded, but most people in this group are selective. And then you can discuss during the tutorial the feedback, and you're not just hunting around, but you can come together as a group. Okay, you had the problem as well?
Yeah, I tried to resubmit I could not resubmit my own, because I submitted one at 11 hours, and I thought 11 hours and 12 hours, and I tried to resubmit, but it didn't work.
I see. Again, you should maybe write an email to Nick. And okay, very good. What do you want to say to
Yeah,
that?
you can resubmit, but you have to remove your previous submission first.
I was not allowed to remove my submission due to reviewing, to self-reviewing. Otherwise, yes,
Did anyone try to resubmit their own
I
thing?
resubmitted
You managed to resubmit.
and I managed.
So maybe you already started your review? Okay.
yeah, I checked out what it was because I'd never seen a self-review, so I pressed the button and said, okay, that's it.
Okay. Okay, but it's good to hear that everyone else could work through this. And yeah, I mean, feedback fruits is always, you don't really know. There are so many features and so on. Yeah, but maybe next time, yeah, maybe speak with Martin in the break and see how he did. So did you use the book yet? Did you find it useful? Okay. Okay, good. That was it for questions for now. Yeah, so we went through post sets the last time. A part of it you read at home. Then we went to combinatorial counting, and we learned about the binomial theorem, the binomial coefficients. Yeah, and we counted some basic things like injective functions and functions overall, or the number of subsets of n elements. And now we go to multinomials. Okay, so and we start with an easy example. So how many possibilities are there to rearrange the word Mississippi? Okay, those of you who've already read ahead know the answer, but it's maybe kind of a not so difficult exercise, but it leads us directly to the definition of multinomials. So if all letters would be different, how many ways there would be to rearrange those letters? Which we denote as?
Factorial, so
Yes, and so these are 11 letters, so we have? Very good.
in this case, you do like
We will come to this. So now we have the letter I, right, which we have 4 times. But actually, for any word that we create in this way, the letter I, right, we double count it because we could permute this letter I. How many ways can we permute this letter I? 4 factorial times. So we double count it because all of those possibilities we counted 4 factorial many times. So we divide by 4 factorial. The same with the letter S. There would be, again, 4 factorial many ways that we rearranged it, and all of those combinations were different. And the letter P. And then the answer is, I don't know. Okay, I've written down the answer, but I guess it was something like 2,500. I've written this down. Okay, and this is kind of the motivation for this multinomial. So you don't have just 2 things below, but you have 3 things below, or many more things. So maybe if you had just 2 letters, right? If you had just A's and B's, right? So maybe you have a number of A's equals 5, a number of B's equals 10. The ways of rearranging it would be 15 choose 5, and you divide by 5 factorial and by 10 factorial. So maybe this is how you can motivate these multinomials. So in general, n choose k1 up to km is n factorial divided by k1 factorial. Okay, and then there is a multinomial theorem, again without proof. So we sum over all these possible ways to add up these ij to n, and then get x1 to the I1 times xk to the ik. So I don't want to give a proof, but maybe some intuition. So we have this first multiplier, the second multiplier, I guess factor, you would say. And you know, here we pick out one, and here we pick out one. So in each of those, we pick out one, right? And then we're looking for, okay, how many ways are there to pick out, let's say, x1 I1 times, x2 I2 times, and so on and so forth. And yeah, that's how you can derive this. Matousek says that you should use generating functions, which is one of the later topics of the book that we will not cover in class just because we don't have enough time. But it's a topic that yeah, is maybe if you're more curious about it, you can look at it in your own time. So so Matousek says you should use generating functions. I would just propose a combinatorial proof. But here we don't do the proof. Okay. Cool. Yes. You know, these are all the ij that sum to n. So maybe I can write it differently. I could also say, no. So let's say I have this set S, which is just the I1 up to ik, such that sum of ij, j equals 1 to k equals n, right? So that is a set. And so these are, I guess, this ij should be larger or equal 0, and the ij should be integers. And then really what I meant to write here in shorthand notation is I sum over all I1 up to ik element S. Thanks for the question. Yeah, sometimes I abbreviate a little bit. So please ask me if things are unclear. Is that now more clear? Okay. I should not do too many abbreviations. More questions? Yeah. Yeah.
first you pick where S should go.
You first pick what?
First from 11 places where letter could go, 4 places where S could go. And then from the remaining 7 places, you pick where the second letter would go.
So you say.
After 11, choose 4, and then 11 minus 4, choose 4.
So then 7, choose 4, and then 3, choose 2. So you say, okay, first I pick the S, the positions of the S. Then for the remaining, I choose the position of the I. Then for remaining, I have the position of the P. And then there's only M remaining. And that has only one possibility left to go. Yeah, that should add up to the same, no? Yep. Very good. I like to look at things from different perspectives. Okay, so now we go to the next section, 3.4. We deal with estimates. And yeah, we start with this little example, the harmonic numbers, and we will give better estimates. I mean, on the one hand, so for instance, these harmonic numbers, they come up in real life, right? So I had a paper and I suddenly saw these harmonic numbers and I didn't know how to estimate them. And if you don't know these are the harmonic numbers, you're a little bit screwed, because I didn't have discrete mathematics when I was a student. But I think they're actually useful and come up surprisingly often. So yeah, we have 1 plus a half plus a third plus 1 over n. Who has seen those numbers before? Okay, so maybe I'm not telling you too many new things here. Now I want to estimate them. But I need a little bit more space, so I write them like this. So I just write them like in these groups here. So far, so good. And I give upper and lower bounds. So clearly, this is at least a half. And you can see that, I mean, for one, it's easy that this is a half, it's kind of a silly of a lower bound. And for a half, you can also see it. And here it becomes interesting. So a third and a quarter are at least a half. And now if you don't see it immediately, or maybe you see it immediately, but actually you should see it in a systematic way, which is a third is larger equal than a quarter. You have twice a quarter, which is half. And now here you have all these terms. Aha, I think I did this incorrectly. So you have here 1/5, 1/6, and so on. And you have 4 of those terms, and each is at least 1 over 8. And here you have all these terms, which are at least 1 over 16. And you have 8 of these terms. So the number of terms double each time, and their size halves. So that's why we get the lower bound. And now as the upper bound, we have 1. And then instead of, so each of these terms is smaller than the term above. So each of those terms right, is at most a quarter. Each of those terms is at most 1/8, and this is how we get the upper bound. I see some confusion, on some face, yes?
How can 1, 5, 1, 6, 1, 7, 8 be more than 1/4?
1. No, each of them is at most 1/4, right? And then there are 4 of those, so we are upper bound by 1. Yes?
The right hand side could
In one case, it's strict,
how
but otherwise it's not strict.
yeah, first case. Other ones are
Sorry, yes. I mixed up strict. So they are never strict except in the first case. That's what you meant, right?
always strict.
Yeah, thank you. Okay, it's too early in the morning. Yeah, so in the first case, it's non-strict, otherwise it's always strict. And then we get Hn. I always dislike these yes, these how to say this is rounding, because I always feel I maybe rounded incorrectly, but then we get this bound. Yeah, and if you, so for instance, for me, in my research where it came up, I wanted to upper bound the running time of some algorithm, right? And then my algorithm somehow, he, I don't know, is it male or female? The algorithm, it had to do less and less work in each iteration, and that's how I came up with this harmonic series, and then I got this upper bound. And usually for me, this upper bound is good enough. But then we go to asymptotic comparisons. And so this is a little bit of a non-standard notation, which has purely pedagogical value or educational. And maybe you don't like it, and maybe it doesn't have educational value, but at least it has a purpose of having educational. So this is not a normal inequality, it's like a curly inequality. I think it's difficult to draw precisely, so I just say it. So this just means that at some point, Fn is always smaller than Gn. It could be that infinitely long, or for zillions and zillions, Fn is larger, but at some point, Fn is small. Notation is clear. And this is kind of thinking about the asymptotics. We don't care for the first finite things. We only care for what's going to happen very far in the future. So by the way, who already knows about big O notation? Okay, let me do the reverse. Who hasn't heard about big O notation? Okay, some people are in between, they never raise their hand. Okay, but yeah, so I guess many of you will have heard this already, and then you can correct me if I forget something important. So what we can say, F equals big O of G. So here we just say things go at some point, it's higher than the other. But in this big O notation, we also allow that there is some other constants n0. And we don't really have to be larger than f, but we can have like just like in the same range. So we have this constant c in front of us that can help us. So this makes sense. Maybe let me give an example. So we can have the function n squared and the function 1 over 10 times n squared. So this is maybe our f, and this is our g. And sorry. And here the g is we have f equals big O of g. And what happens is g is never ever larger than f, right? But the only difference is the leading constant here. And so the big O says, okay, we stop caring about these leading constants. Okay, I've looked at two more examples which maybe illustrate how to operate with them, but also some criticism. So we can have, for instance, n plus 10 to the 10 to the 10. Right? So these are more, this is larger than the number of atoms in the universe by, number of atoms in the universe is nothing compared to this number. But still, this is O of n. Right, so what we need to be careful with is if we have this big O notation, sometimes we really don't know how large these constants are. And while in many cases they are mild, there are also a lot of cases where they're astronomical. And then it is more of a theoretical result that sometimes is O of n, right? But it can still be helpful because you can, for instance, prove the existence of something or show that some probability eventually becomes larger than 0 by just knowing that this is just a constant and we can ignore it. Okay, and another example, just to see how you can work with these things. So we have here these two functions, we multiply them, and then if we know what big O notation means and we are used to operating with them, we see that here the dominant term is n to the 3, here the dominant term is n squared. We multiply them and we have O of n to the 5. So let me maybe extract a little bit of the discussion in Matousek. So what's the purpose of this big O notation? We could just ignore it, right? Yes?
Comparing the speed with different.
That's very specific, maybe more general. Yeah, but that's correct, yes. So we can use it for comparison. So maybe let me maybe give other the opportunity to say something. So what could be another purpose? Yes? Finding upper bounds. I could find upper bounds without the big O notation, no? Why should I have the big O notation?
Comparing the group, not necessary.
This is very specific. I'm looking for just very general purpose, like yes? Giving estimations, yes. So for instance here, right, we have this harmonic series. I should write down the name, I guess. Harmonic numbers. If I give you this, right, that's an explicit formula. It's very precise. Why should I work with an estimate? It's gonna converge to infinite. I mean, that's what it tells us here, right? So if you read this, do you know roughly how large it is? If you read this, do you roughly know how large it is? And so what's the reason behind it? Nothing to do with differentiation. Okay, let me give it away. The point is simplification. Right. So we can say, oh, our algorithm has this running time. And I was like, oh, I don't know that. But if I tell you, oh, the algorithm has log n running time, everyone's like, ah, log n, I know that function. Yes? Yeah, so this one is just because I have always a 1 here. And then I wanted to just, yeah, it's just, also you shouldn't write it like this, because then people don't know if this +1 is in the brackets or not. So a better way of writing is this. But what I want to say, I put this times 1 here because this is like the constant here, which happens to be 1, which just can be ignored. Yeah. Yes? You could add brackets. So yeah, so that's a good point, right? So you could write this in 2 ways. You could write log n bracket +1, or you could write this. Which one do you prefer? Down, why? Less symbols, yes. So I kind of forbid all my co-authors to use sub-indices because it's usually not needed and confusing. So you should always try to think, how can I write things in the simplest possible way? And here comparison is also to known functions. And simplification both of the result and also of the computations. Yes? Yeah, so if I say log, it usually means log to base 2. Of course, it makes a difference. Yes. So simplification of computations. But also of results. And so the criticism, yes? Yes. Yes.
So I guess definition of what is given right now that really provide like don't know if it's like just of it, like a true destination.
Yeah. So yeah, so we want to find simplifications that are simple, but also precise. So we are kind of in this trade-off, right? That we could find simpler upper bounds, but then I can say, oh, this is O of n by, right? That's a very simple upper bound, but it's a very crude one. And I can say, oh, this is 1 plus log n and some complicated formula. That would be a more precise upper bound. And so you're always, the upper bound that you're using, you always look at how simple is it and how precise is it. That's the trade-off you have. And yeah, the criticism is the possible humongous constants. Yeah, and then yeah, if it kind of becomes meaningless, so we should be aware of this. And there are lots of results in theoretical computer science where we know this algorithm runs in linear time, but for n equals 3, the constant is so large that you will never be able to neither implement it nor execute it. Okay. So there are some useful facts about this. So n to the alpha is equals O of n to the beta. If and only if alpha is not equal to beta. N to the c is O of n, alpha to the n for all c and a larger 1. And then log to the c n equals O of n to the a. So basically this says polynomials grow faster than logarithms. Polynomials grow slower than exponential functions. And polynomials, if you know the exponent, you know how fast they grow. And that's usually good enough to do all types of estimates. If you want to have a fun exercise, try to find a function that grows faster than any logarithm and slower than any polynomial. Yes? What is log linear? No? So A could be also something like 0.1. So yeah. So this is A is just larger than 0. You can think about that. Okay. Another example. Yeah, you can add up all of these. So Matousek develops some formulas for the sum of 1 to the 3 plus 2 to the 3 up to n to the 3. And so some simple estimate using this big O notation is yes. No, that's incorrect. In the back, n to the 4, yes. So basically, each of those things is upper bounded by n to the 3. This is upper bounded by n to the 3. And then this is the same as O of n to the 4. And you have to be careful here, because if I have n to the 3 plus n to the 3, right? It says n to the 3, O of n to the 3. But if you have n of those, you have an n to the 4. And so what sometimes happens that people make these proofs by induction, and then in this induction step, they just have this extra factor of 2 or something, and they hide it in the big O notation, and then they forget a linear factor. So you need to be a little bit careful when you do proofs with big O notation. That it's really just a constant and not, if you repeatedly add something to that constant, then it's not a constant anymore. And there's also a lower bound here. And the lower bound goes as follows. We kind of estimate the first things just by 0. And then we have n over 2 to the 3. So we just take the right half of all of these entries. And this gives us n over 2 to the 4. Yeah, which is, not big O, but it's, I guess, the other notation, which is omega to the n to the 4. So omega, I don't want to define, but formally, but it's kind of the opposite of O. So we say F equals omega of G if and only if G equals O of F. Is this correct? Yes. Okay, now I did formally define it. Then we have F equals little o of G, which means that F divided by G goes to 0 with n going to infinity. And F equals theta, I should say. Are there any Greek-speaking people here? Okay, I had like I once said theta, and then this Greek person shouted out, no, you mispronounce it. So my apologies for that. So theta is the same as O of G and F equals omega of G. So this means they have like the same asymptotics up to the leading constant. Aha, yeah, we go with only to 45, right? I get confused. Then, yeah, so then maybe it's a good time to have a short break. I would ask you to mark yourself here on the scale so that I have an idea on what your workload is. Please think first where you want to put your marker before you look at what everyone else did, because you should try to have an independent estimate. Okay, then we continue in 15 minutes.